We're going to go back today and revisit this topic of Taylor and Maclaurin polynomials and extend those to what we call an infinite Taylor and Maclaurin series. So in a previous lesson, we used the notion that if we could write a polynomial that has the same value and same value of derivatives up to a certain point of a function like e to the x or cosine x, then it becomes a very good estimate of that function for a little while. Now the question would be, could we extend this and make the polynomial longer and longer and longer and ultimately model the function indefinitely? And for a lot of cases, the answer is yes. That's what the study of Taylor series is all about. So as we go through today, you're going to see a lot of familiar terminology. We're just going to extend it to make it from a finite length Taylor polynomial to an infinitely long Taylor series. You should recognize a lot of the parts of this definition. It's the definition of a Taylor and Maclaurin series. Notice that if you just look at the beginning of the string of terms here, it looks a lot like our definition of a Taylor polynomial. That is, each successive term is a value of the function or the function's derivative. And the coefficient is that value divided by a factorial. And all we're going to do now is just extend that with basically indefinitely and call this a Taylor series. We can still use the terminology that the series is centered at some number a. And if that number a is 0, that Taylor series is often called a Maclaurin series. And so we're going to use the definition today to study 4 functions and their Taylor series in particular. And these are the 4 that you really need to memorize going forward. You guys who are taking the AP test, they're expecting you would know these 4 by memory so you can use them to do other tasks. Okay, those functions are 1 over 1 minus x, which you've already seen in the prior lesson, but then the other ones you're going to see today are sine of x, cosine x, and e to the x. Now to make it go a little quicker today, I'm going to, on each of the slides, already have worked out the value of the function and the first 3 or 4 derivatives at the value of a that's going to be the center of the polynomial. These are all going to be Maclaurin polynomials today, so the center will always be 0. And the only thing I'm going to have to write on the slide for you together, with us being together here, is to write out the first few terms and then decide what the general term looks like. Okay, so we're going to visit sine x first. I've written out the value of sine of 0, or f of 0 being sine of 0, and then the first 3 derivatives. Maybe I should write the 4th one in there too. And so the 4th derivative would be back to sine of 0, which would be a 0 again. Okay, now we're asked to write the first 4 non-zero terms. Now remember, the general term of any Maclaurin series is the nth derivative at 0 over n factorial, and then x minus 0 to the n. So all we have to do is find, what we're going to want to do is, after writing the first 4 terms or so, see what how the pattern will be written. Okay, well, according to this list, every other term is going to be 0 for a while. So, or every other term will be 0. So the constant term will be 0. Then we'll have 1 over 1 factorial, x to the 1. Then we'll have a 0. That'll be the x squared term. Then we're going to have minus 1 over 3 factorial, x cubed. And then we're going to have 0. Now we're asked to write the first not four non-zero terms. So technically these ones do not count for that task. We want to keep going until I get four terms that aren't zero. But this allows me to see a pattern here, and that is with the sine function, every four derivatives goes around this cycle. So what's going to happen is every odd derivative is going to be either a 1 or a minus 1. Every even derivative is going to be a 0. So I'm going to say the next term after this one is going to be a positive term. It'll be a fifth degree term, and it's going to be 1 over 5 factorial x to the 5. The following term would be a 0, and then the seventh degree term is going to be a minus 1 7 over 7 factorial x to the 7, and that establishes the pattern using the first four terms. So what I would like to do now is just look at the non-zero terms and write a summation formula just for those. Okay, so my formula is going to account for the fact that only odd degrees are going to show up, and every other term is alternating signs, right? So I would like my series to start when k equals 0, and I want my first term to be a positive term. Okay, so that means I can allow k to be the power of -1. Now I want all the powers to be odd. And so one way to do that is to notice that an odd number is just an even number plus 1 or minus 1. And in order for this to work well, when k equals 0, producing the answer 1, I want x to be to the power 2k plus 1. That way, when k equals 0, it's 2 times 0 plus 1. And my factorial copies the power of x. So it'll be 2k plus 1 factorial. And this will produce these terms like it is. So we're going to call that the formula for the Maclaurin series for sine x. We'll do the same thing for cosine x. Now what we're going to notice this time is the function value at 0 is 1. And then we're going to alternate zeros, -1s, 0, 1s again, just like with sine, just will be one off. And so what we're going to find this time is all the even power terms are non-zero, and all the odd power terms are going to be 0. Right? So my constant term will be the 1 this time. Then I'm going to skip the x to the first term, and my next term is going to be -1 over 2 factorial x squared. And we're going to keep alternating like this. And I'll get to the fourth one here, would be actually the sixth degree term, which I didn't have in my list, but I know it's coming. It's going to be just like this. And so I'm going to write a summation rule that follows that pattern. This time I want only even powers to show up. I still want to start with a positive first term. So I think x to the 2k, because x to the 0 would be 1. That gives me the very first term. And then the coefficient is always dividing by a factorial that models the same as the degree of the term. So 2k factorial ought to do it. So this is how we typically write the Maclaurin series for cosine x. The third one we're not going to spend a lot of time on because you've already seen this one. Now we have talked about this function and its power series, not in terms of it being a Maclaurin series, but if we did use the definition and worked out the first few derivatives, this in fact would be that Maclaurin series. This we also recognize as the geometric series. And so the same one we were using in the prior lesson is the same one we would get by using the definition. And so we can just say we already know that one. So finally, let's spend a little time working on with our function e to the x. This one should go quickly too, because every derivative of e to the x is e to the x, and every derivative evaluated at 0 is going to be 1. So the first 4 terms are pretty easy to write. In fact, I'll just go ahead and fill them in. Now this now gives us the first 4 terms, and it gives us a nice pattern already too. Every derivative is equal to 1. So the pattern just goes, every coefficient is 1 over a factorial. The factorial is the same degree, same number as the degree of the term. So I will write this one starting at k equals 0. And basically it's 1 over k factorial. And actually, we're just going to write x to the k right up here. Okay, so we're going to write x to the k over k factorial. This is commonly how we write the Maclaurin series for e to the x. Okay, well, if we were in class, we would probably have a handout for you to fill these in on. I encourage you to make a list for yourself. These are the 4 Maclaurin series that you really need to memorize. Now, what helps me in memorizing them is we've already worked with this function 1 over 1 minus x and know it's the geometric series. Now, what helps me a lot with sine and cosine is, if you remember that probably in pre-calc and even in last year in calculus AB, we probably talked a little bit about sine and cosine being even or odd functions. So if you remember that the sine of x is an odd function, remember that has to do with the symmetry of the graph. The polynomial for sine of x has only odd degrees. And cosine is an even function, and its polynomial has only even degrees. That always helped me when I had to memorize it, along with the fact that they're alternating and always start with a positive term. Now, for e to the x, it's helpful just to know, hey, e to the x is its own derivative. Evaluating it at 0 always gives you a 1. And if you're familiar with the definition of a Maclaurin series and how the coefficients work, that's an easy one to remember right there. It's always going to be 1 over k factorial times x to the k. We'd also probably spend quite a little bit of time discussing the radius of convergence for these. The first one we have already talked about in great detail. The radius of convergence in that first one is 1, centered at 0. And so the interval is all numbers between -1 and 1. It turns out we could prove each of these using the ratio test, but we will leave that part for now. I'll just tell you that the radius of convergence for the other 3 is actually infinite. If the polynomial or if the Maclaurin series is made long enough, it converges on the entire real number line to the functions that they're based off of. So what we're going to spend a little bit of time on then today is to take these basic building blocks and build other Taylor series and Maclaurin series using the process of substitution. So we're going to do that a couple of times here. Let's start with the function e to the x and use it to make the series for e to the 2x. So from now on, you're not expected to use the definition to build your Taylor series. You're simply expected to know the Taylor series for the more basic version of this function, which is e to the x, and then just substitute into it. Okay, so the thing we're supposed to already know ahead of time is that the Taylor series for e to the x is this. Okay, I'll just write out again, it sometimes helps just to write out the first few terms. And I'm going to do that. In fact, I might even just write the general term again. 1 x to the k over k factorial. So now, if I would like to know the Taylor series for e to the 2x, remember that the same principle is for all power series. We can substitute into the known one the quantity 2x in this case. You could think of this as a composition. So if I want the series for e to the 2x, I'm simply going to take my series for e to the x and replace every x with 2x. Okay, so we're going to go like this. And you see how this is going now? So if I want to go to the general term, all I've got to do is take that general term for the original series and replace the x with the 2x. So it's essentially going to go like this, 2x to the power k over k factorial, and still k goes from 0 to infinity. And remembering that the radius of convergence for this original Taylor series up here was infinity, so this one still has an infinite radius of convergence here. And let's do one more for today. Let's take the series for sine of x and then make the series for x sine of x. So what we'll remember here is the series for sine x is our basic idea first. And again, the memorization tool was sine x is an odd function, so I know that its power series has only odd degrees. So that way I know that the first term is that x to the first term, and then it's an alternating series after that. Okay, remember that the general term was -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. So now what we'd like to do is just multiply that by x. Okay, so the series for x sine x will now be just to take the power series for sine x and multiply it by another x. So if I want to write out the first few terms, here we go. So it'll be x squared, and then 1 over 3 factorial is now the coefficient of x to the 4. 1 over 5 factorial is now going to be the coefficient of x to the 6th. And minus 1 over 7 factorial is going to be the coefficient of x to the 8. And so one way to look at this is you took the general term that was up here and you just multiplied it by another x, you'd get the general term for this one. So I'll squeeze that in down here. And the powers of x will be one bigger now. So instead of x to the power of 2k plus 1, we'll call it x to the 2k plus 2. Okay, so it'll be 2k plus 2. But then the factorial now is still going to be 2k plus 1 factorial. There's our new general series. We'll stop here for today. I know this has kind of been a long one again. We'll probably give you a couple more examples on Monday, and we'll go from there. Okay, we'll see you guys on Monday. Thanks.